It is my great pleasure to begin with Professor Lahav. Professor Lahav is the person chair of astronomy at University College, London, and leading researcher in the study of the dark sector of the universe. As a co-founder of the Dark Energy Survey, DES, and long-serving chair of the Science Committee, Professor Lahav coordinated the efforts of hundreds of scientists mapping hundreds of millions of galaxies, producing one of the most comprehensive proofs of cosmic acceleration and the distribution of dark matter. His work focuses on characterizing the properties of dark energy and testing whether it arises from a cosmological constant or from modifications to Einstein's theory of general relativity. A pioneer at the interface of astrophysics and data science, Professor Lahav introduces advanced machine learning and artificial intelligence techniques into cosmological data analysis, including early applications of neural networks in the early 90s for galaxy classifications and photometric redshift estimation. By combining massive observational surveys with sophisticated statistical methods, his research aims to shed light on 95% of the universe remains invisible. Today's question is deceptively simple. Is dark energy evolving with cosmic time, but embedded within it is a deeper inquiry? Are we observing a constant or witnessing a paradigm in transition? Professor Lahav, we are honored by your presence. The platform is yours now. Thank you.
Thank you very much for the very kind introduction. I hope you can hear me well.
Yes.
It's a pleasure to participate in this very exciting program. And I understand that over the past 2 years, two days, you've heard very nice talks introducing many of the topics. And today I'll zoom in on one ingredient of the universe, a mysterious one, dark energy. Okay, very good. So just as a quick introduction, I should mention that, yes, I'm based at University College London. Previously, I spent, nearly 20 years in Cambridge. And I'm also a member of a number of big collaborations, in particular the Dark Energy Survey, DES, and the Dark Energy Spectroscopic Instrument, DESI. In fact, you can see if you can see the arrow, this is the DESI catalog or map. Each dot is a galaxy. There are now 46 million galaxies which measure spectra. On the right-hand side is a map produced from the Dark Energy Survey. And this is actually this region you see here. So this region is actually encompasses a map of the dark matter. So you may puzzle, if it's dark, how could I show it? It is a reconstructed map using weak gravitational lensing. We'll come to it later. Just for orientation, you can see there the Milky Way from the Gaia satellite and the Magellanic Cloud, this large and small. And of course, almost everything we do is within a paradigm or framework that was introduced by Albert Einstein, and we'll be more specific about what he said about dark energy. And in any case, we see him here experimenting gravity. I don't know if at the end, if he survived being on the bike or not. Okay, so moving to the next slide, I'm going to go through a brief history of cosmological constant and cold dark matter. I know that especially this forum, your university, has a lot of interest in philosophical and historical elements. So I'll do my best as a humble astronomer to comment on that. I mentioned I'll mainly show results from two projects which are, in a very mature stage. In fact, most of the results already published. but I'll also talk about the future. And the question is really, as was also introduced by the session chair, is dark energy just a constant with time? And by that I mean the density energy of the density of the dark energy, which means it's just Einstein's cosmological constant, or is it evolving? And of course, the question is, what's next? Okay, what are the expectations? Can we pin it down better? So this is very much of an open question. I would like you to appreciate that point. I'll allow myself to slightly deviate from the standard physics type of talk and talk a bit about the social value of studying such elusive topics as dark energy. And also I'll comment on AI, how it can serve us in cosmology, but also maybe to say that cosmology is helping in AI because we have all these big data sets and big questions. So most of you probably are familiar with the concept that there was a Big Bang 13.8 giga years ago, 13.8 billion years ago. And since then, the universe is expanding. There was a period, a very brief period called inflation at the beginning. And then the universe carried on expanding. And about 25 years ago, there were measurements that suggested that the universe at present is accelerating. And this is pretty much still the picture. If you look at the central kind of cake, this is what the different slices are, the budget of the universe, only 5% are ordinary matter, and now we think 25% is dark matter, cold dark matter, and 70% dark energy. I have to emphasize two things. One is this is the composition of the present epoch, okay? In earlier times, the universe was denser, so dark matter was more important. Also, I have to say that this picture is not perfect, as we'll discuss. There are some tensions. So will these tensions disappear? These tensions, that means disagreement, will it disappear, or would it persist and lead to a new paradigm? I have to say there are probably people at different academic age in the audience. I say, when I did my PhD in Cambridge in the late 80s, the story was quite different. Everybody talked about the standard model where there were 5% baryons and 95% cold dark matter. So at that time, the dark energy was believed to be zero. It was not known as dark energy, it was cosmological constant. And if you would talk about cosmological constant in a lecture, people would probably laugh at you. And then I was fortunate enough, in the early 90s already there were some issues, and myself, I wrote a paper in 91, but then it was really 98, 99 when the two supernova teams showed us that indeed there is something which causes the acceleration, and it's probably that type of something, dark energy, or maybe a bigger name, a wider concept, which includes the cosmological constant. Cosmological constant, of course, goes back to Einstein. I recommend reading this paper. It's in German, but you can find the English translation on the website of Princeton University. And it's really in 1917 that he put this paper. He introduced lambda for a number of reasons, not just one, but one of them, he didn't like the idea of expanding or contracting universe. So he introduced lambda, as we'll see in the next slide. So this is Einstein's equation in full glory. In fact, on the poster of your conference, I saw the same equation, and I was quite, in a way, interested to see that you also put lambda, so this is the cosmological constant, on the left-hand side. These R you see there, they describe the curvature, and Einstein himself in 1917 put it on the left-hand side. On the right-hand side is what's called the energy momentum tensor, which means you put something there, it would affect the curvature. That's what John Wheeler told us, that matter and energy tell space how to curve, and then space tells matter how to move. So it's interesting. I want to emphasize that point that Einstein put on the left-hand side, you put it on your poster left-hand side, which I interpret as kind of another constant of nature, a bit like big G or C, right? But in fact, most of our colleagues, especially in particle physics, would like to put lambda on the right-hand side and absorb it into T mu nu, and then it has a meaning of energy, and that's why the name dark energy. But to be honest, we still don't know if it's on the left-hand side or right-hand side. It's also another interesting exercise is to take that equation, which is very complicated, and take the limit of weak field. And what you get then is a very nice equation, and most of us know it from our childhood, from school, that acceleration is minus gm over r squared. So that's the force that got the apple to fall on Newton's head. But you have a residual here, which is this lambda over 3 times distance. And if lambda is positive, it's a repulsive force. So in that interpretation, you have the acceleration, things are bringing you together, and you have the lambda force pushing. You may ask me, or students like to ask, can we see it, in day-to-day life? No. This term is very, very small. So when we take airplanes, whoever designed the airplane and the motion of the airplane doesn't care about that. Planets in the solar system, again, not really important. However, and I was surprised when I saw it, we did a paper with a student some years ago, when you look at Andromeda and the Milky Way, when they fall towards each other, this force is actually there. It's repulsive, and it changes some of the dynamics of the system. So on scales of megaparsecs, millions of parsecs or millions of light years, this is actually important. There's another interesting point, which is little known, that actually Newton in Principia suggested a linear force. He didn't call the constant lambda, but he suggested that, and he even said that it was very remarkable. And you can read what he said, or we also you can find on my website a popular article which explains why he suggested two forces. Einstein himself decided that that's not true. What he put in, because a few years after he suggested 1917, Hubble and Lemaitre discovered the expansion of the universe, and Einstein felt very upset about it, that he basically put a constant which was not needed. On that hand, his friend Arthur Eddington, and here they're seen sitting together when Einstein visited Eddington in Cambridge. Eddington actually liked it. So I think this is the original paper, 1917, I mentioned, and you can find it on the Princeton website. And you can think of it some modification, really. But the key point is that Einstein, he added a constant, but you have a constant that could have any value. He chose a value which is 1 over the size of the universe squared, and this gave him a static universe, which is neither expanding nor contracting. But he somewhat overlooked, and of course we should respect Einstein, but he somewhat overlooked that this lambda could be any value. So you can have a value which gives you a static universe, but you can also have a value which gives you an expanding universe or contracting universe, okay? In any case, it's quite remarkable, this paper he wrote, 1917, is what is driving now the work of hundreds, if not thousands, of scientists in projects which cost billions of dollars. So I think it's all very exciting. We're in an exciting time. And there's this question about left or right hand side. And I mentioned the missed opportunities. He could have said that it's, it could have a different value, which would give acceleration. But the other point which you overlooked, which other physicists at the time showed that static universe is unstable, so it wouldn't have worked. Anyway, so I hope you get the idea. People ask, was Einstein right or wrong? So he was right in introducing this constant, and the data more or less agree with that there is such a thing, but he was wrong on picking up the wrong value for that. This would be my short summary. Now, for those of you who want to see a bit of equations and formulation, you probably remember that any substance in nature could be characterized by an equation of state, and it has pressure and density, and the ratio, if you put the speed of light squared there for units, is called W. And for example, if I just look at just matter, W would be 0. But if it's, for example, radiation, it's a third. Now, we can do a textbook exercise and ask, if I tell you that's an equation of state, what is the density? How does the density change if this W is a constant? And you have that equation. So if W is 0, the density drops like the cube, 1 over the cube of the scale factor of the universe. It's kind of intuitive. If it's a third, it's a to the minus 4, which is a bit maybe less intuitive, but you can explain it in other ways. If it's, so you can make plots of this density, yeah? This is at earlier times. This is the present. So the present, we have 30% matter, that's dark matter plus baryonic matter, and we have 70%, that's the blue point. But in the past, the dark matter was much denser. But if Einstein is right, then you can ask, for what value of W would that rho be a constant? And it's easy, right? It's -1. So dark energy is a strange, or cosmological constant is a very funny property that it's actually negative. Now, the question, what is it? So when it's exactly -1, it's lambda. If you force it to be a constant, measurements show that it's about -1 to 2%. But if you allow it to vary with time, you find that it's more comfortable deviating from that value. And that's the title of my talk, right? Is it the case? And that's the title of the rest of the lecture. So I told you there is some signs of that lambda. Einstein talked about 1917. Occasionally it appeared, you can see literature from the 50s, from the 60s of last century. It comes and goes. I remember one calling me when I was very excited as a young man. He said, don't worry, every cosmologist is going through a lambda phase. But, it seemed to persist. And there are these, very important papers by Jim Peebles, who won Nobel Prize, Weinberg won Nobel Prize, not for that, but they are well-known physicists. And that's while I was in Cambridge, one of my mentors there, Statio, did some work. He did not measure directly omega matter. He measured omega matter, but he did not measure omega lambda, sorry. He measured omega matter, but he found omega matter to be about 0.2, and he did 1 minus 0.2 equals 0.8. So he said, must be a lambda of 0.8. Now we would say 0.7. And me as a young, naive student, I did a little paper in 91, together with Lilie, Primack, and Rees, where we also looked at different possibilities of omega against lambda, and we concluded that we can actually not rule out the possibility that lambda is non-zero. Now, what happened then is that a group of 2 teams looked at supernova exploding stars. Actually, they're made of a binary, and one star accretes matter from the other, and then there's an explosion. And this has to do with Chandrasekhar's mass, which I'm sure most of you are familiar with, which was defined by the famous Indian astrophysicist Chandrasekhar, 1.4 solar masses. So this is believed to be the mechanism. In any case, nature has been very kind and produced for us standard candles. So if we believe that the same mechanism is behind every object called supernova, and we do some corrections, we can then learn about it. And that's what happened in the late 90s. two supernova teams could not explain the data unless they put something like a cosmological constant. You can do the same thing with standard rulers. So nature is kind enough to give us some features in the distribution of galaxies, which we call baryonic acoustic oscillations. They also appear in the CMB, and therefore you could basically measure that. So it's geometry. It's geometry. But you can also count the number of clusters in a volume, which would be different if there is a cosmological constant or not. And you can do this technique, which is very beautiful, called weak lensing, that objects in the distance, their shape gets distorted. So maybe if this was almost a circle, by the time we see it, it will have this very narrow shape. And we can look at these distorted images and look at how they're correlated over the sky and learn also about dark energy. So these have been the four primary techniques to learn about the dark energy. And this, of course, has led to all these activities after the supernova discoveries of this telescope. And this is a big array of CCDs on the telescope in Chile. So this is a project I spent nearly 20 years on with many, many other colleagues, about 400, led by Fermilab in the US. And this is a 4-meter telescope where the camera was upgraded, and part of it was built in our basement at UCL for both DES and the other project DESI. That's on a telescope in Arizona, and DESI is actually just about to finish the original plan in a few days, sometime at some point, very, very soon. So there will be probably a press release about that. And that's about, DES collected about 300 million images. DESI collected about 46 million spectra. But this is just the here and now. Rubin on the neighboring hill is a brand new telescope and already collecting data. And so is Euclid, a space mission of the European Space Agency, also collecting data. So those two is a big jump relative to this, but that's how science works. When I was a student, we had thousands of galaxies. Now we're talking about billions. So this is just a summary of some of them. You can see the amount of data. You can see the number of galaxies. I mentioned it will go towards billions. You can see the cost going from 100 million to a billion. And I like to tell our funders that putting $1 billion is a good deal because each image of a galaxy is only $1. I don't know if they buy this argument, but we try. And also you can see the number of scientists goes from hundreds to thousands. So it's a different type of doing science, a bit like particle physics now. I mentioned already these two telescopes in Chile and Arizona. I can only say I was there for a week in 2015, and there was a huge earthquake, 8.3, but it survived. Telescope survived. So shows you how strong it is. It's led by American laboratories, Fermilab and Berkeley, and as at UCL bought the optical correctors, and these are the numbers of objects achieved. This is the camera. It's the same camera, same principles as your mobile phone, but it's using it's weighs several tons. And for those interested, especially also in the history how it happened, we produced this book written by the people who created Dark Energy Survey, and it even includes at the end chapters on philosophy and anthropology, etc. Dark Energy Survey not only looked at the static universe, it also looked at supernovae, and the Nobel Prize to these teams that discovered the leads of these teams, Perlmutter, Schmidt, and Rees, they use 42 supernovae, got Nobel Prize. Now DES can measure 1,500. And you see the light curve, you look at the galaxy, it looks very boring, and suddenly there's an explosion. and this is the amount of light and the decline, and you use the peak luminosity with some corrections to use them as standard candles. So this is visual impression of all 1500, and then you plot what's called the distance modulus against redshift, and you get this diagram, the Hubble diagram. There is data from DES, and that's from nearby stuff. And if it was a perfect cosmological constant, should have been just a straight line, but you can see, for example, the green line shows some deviations from that. Baronic acoustic oscillation, similar story. Its nature is kind enough to produce features which have to do with the competition between the plasma and the dark matter, and it leaves behind some features which you can imagine them as rings, but when we use power spectrum analysis, it's the Fourier, or here's a correlation function. It's the probability of finding a galaxy at a particular distance s from another galaxy. And you see this subtle, it looks a bit amplified here, but it's a very small feature that you see. And it's this feature, which is something like, in some other parameterization, it's of over 150 megaparsecs, that you use as your standard ruler, right? Just the same way you use the standard candles. So these are the techniques. The same thing happens with the CMB, and you can see results from Planck in orange, but also from another project called ACT. And you see, look, it looks like a textbook, picture of these fluctuations against the distance. And so what is the problem, right? So the point is, this is the key, maybe you can think of this as the key slide of this talk. And I'm conscious of the time. I'll try to finish on time in about 15 minutes, if that's okay. What the key point here is that if we so as I told you, when I was a student, late 80s, there was no lambda. Then the supernova people told us you need lambda. Now, if you fit separately the baronic acoustic oscillations from DESI, and separately the supernova from DES, and separately the CMB from Planck or ACT or Space or SPT, another project, South Pole Telescope, each of those three fits the data all right. Okay? The problem is when you try to fit them all together, they fit each of them okay, but it gives omega matter, the thing which is supposed to be about 30%, you see, one gives something like 0.25, one gives something like 0.35. So for the same model, they get slightly different fits. So you know it even from first year laboratory, right? You have three parameters. Do they make sense? The problem is when you put all these three together, the supernova and the CMB and the acoustic peaks in the galaxies, they're unhappy. Okay, so the tension and the need to move to this kind of evolving universe, evolving dark energy universe, is because it's when you have all three of them together, that's what you get. If you say, I don't believe two of them, I only want one of them, you could be happy. You could say it's lambda CDM with omega m of 0.32 or something, and you just be happy. But it's when you're trying to take a more holistic view of using three techniques that it's difficult to fit them all together. So this generated a lot of interest. In fact, exactly a year ago, on the 19th of March, DESI published that, and many authors, I'm one of them out of many, and this generated a lot of excitement because there is this tantalizing evidence for evolving dark energy. And you can see it got a lot of attention in the Guardian newspaper and the BBC. Experiment challenges Einstein theory, and so on and so forth. So you can now, it's a bit like going to court. You can have one lawyer saying it's just lambda, W is -1, and you can have another lawyer saying, no, it's changing, right? So I'll try to do both. In fact, I'm doing some work on that with colleagues, trying to look at the different options. So The thing is, when you have just W, you force it to be W, you get something which is consistent with -1. But you have to be a bit careful that you force it to be a constant W. DESI, you can see if you do this equation of state, I told you when it's -1 exactly, it's lambda. So probably you look at it and you tell me, look, it's not exactly what's going on. It's actually not, it's actually going down. And I say yes, but the best data point is there and it's only 2 sigma away. And also there's some subtleties that the CMB dominates it. So it forces it to be close to -1. But if you do it non-parametrically, you can see there's a tendency of this W to change with time. And that's exactly the next. So this is the second lawyer is saying, I would like to have evolving dark energy. So this is the plot I just showed you how the density changes with time. And it's really weird because this is earlier times. So the universe, if this measurement is correct, gets this density and it goes up and reaches a peak and then declines. And in terms of this region, is actually called the universe a phantom attractive because it expands. You'd think something expanding it will have less, smaller density with time, but this does the opposite. And this is another, those of you who like frequency statistics rather than Bayesian, this is in terms of how many sigma. And this is, by the way, parameterization of this time variation. It's two parameters, W0, WA, and A is a scale factor. So at present, A is 1, so it's just W0. Yeah? I hope you're with me. So the point is, for different combinations of data, you would have, if you're a believer, if you're the lawyer who likes lambda CDM, you'd have liked all the data to be there, but it seems that the data prefer to be further away by something with 3 to 4 sigma. I would say after some recent work, people think it's more like 3 sigma. And then it's your judgment as a physicist. Do you lose sleep at night over 3 sigma? You say there's a problem and maybe there's a new theory. Or you say, well, 3 sigma, there are always problems with the data. It might go away. So this is a very important plot and the main message of this talk that we don't know for sure, but there's this tantalizing evidence or tentative evidence, intriguing evidence of evolving dark energy. So there are ways of rescuing. If you are the lawyer who likes lambda CDM, you will come up with all kinds of explanations. Data were corrected, improved, and then it brought the supernova results from 4.2 sigma to 3.2 sigma. Other people are very worried. This is a group from South Korea. They're very worried about the properties of the galaxies, of the host galaxy. How does it correlate with the luminosity? The cosmic macro background, there are details about the statistics, but also there's a constant called, not a constant, a parameter called tau. That's the optical depth to ionization, and depends what you put there in the CMB, things can move around. So if you put a higher one, it helps again with lambda CDM. And some people even are prepared to sacrifice the curvature of the universe, which we like to believe is 0 for that. So I made a very simple plot here. It's a bit crowded, but I just want to show you with all these options. No, the scale factor, it's only when it's lambda that it goes. I plotted it. I'm being a bit, usually you see plots ending at present, which is here. This is the beginning, 0, and that's after 13.8. Here I plot it all the way to 17 gigayears. So I look into the future, and I'm basically saying the universe will expand forever in all these cases, all these measurements, even if it's not just lambda, but other values which are consistent with the data. But it's only in lambda that you'll see this amazing exponential growth with time. And you can look at other parameters there. And this is just zooming in because people ask, okay, with these new results that's evolving in time, will the universe collapse? Will it have a big crunch like in this toy model? Okay, this toy model, the dotted line is not a measurement. You start somewhere and it expands and then collapses again, which could be, it's not in contradiction to Einstein's theory. But it looks like even if you like lambda, as I said, it's an exponential growth. If you like this W0, WA with the measurements of Des and Desi and so on, it's not as dramatic, but it will still expand forever. So I'm sorry to disappoint those of you who like big crunch. I myself would have liked to have a big crunch, but nature maybe wants something else. And I'm doing this work with a colleague, Paul Shah. We'll publish it hopefully soon. So I'm getting there. So what is this dark energy? Is it just we're making some mistakes with the data? Is it just lambda? Does it change with time? I haven't told you, those of you who are particle physicists know that in particle physics, if you calculate, it should be the energy of the vacuum. How come vacuum has energy? Because even harmonic oscillator has an energy in quantum mechanics, the ground state. If you add all these modes, you get a huge value of dark energy, much more than what we measure. So what's going on here? And is this a signature of modified gravity? Maybe it's an inhomogeneous universe. We can also move to the more esoteric work, and I think there are talks at your conference about multiverse and the anthropic principle. The universe would not be the way it is unless we were here to observe it. So, many possibilities. There's always the unknown unknown. Maybe someone will give you a talk 10 years from now and will tell a completely different story. So I listed here a few open questions. Is it on the left-hand side, as in Einstein paper and on the poster of a conference, or is the right-hand side? Could it be W less than -1, phantom, as some measurements suggest? And could it change, with W? When do we decide we know the answer and we stop? How do we live with this discrepancy of 120 orders of magnitude? But maybe there's a room for a new theory, and some people speculate maybe this lambda, which is just one parameter, maybe it hides, maybe behind it, there's lots of kind of unknown physics, and maybe that's also the link between general relativity and quantum mechanics, right? Maybe that's also, and maybe, who knows, maybe thermodynamics or some other branch of physics which we don't even know exists yet. And maybe it will take another 100 years. Lambda has been around for over 100 years. Maybe we need another 100 years to figure it out. I know it depends. There's also the question, which I'm sure is true in every country, and there recently have been some budget cuts on this kind of curiosity-driven science. And I wrote an article with an economist in Oxford, an economic historian called Avner Ofer, and it's in the Royal Astronomical Society journal, Astronomy and Geophysics, of February. We wrote it a long time ago, but it appeared in the month that there were just cuts in the budget in the UK for astronomy and particle physics, so it's funny timing. In any case, we're trying to explain why it's so important for the society to have even this esoteric topic. It's because we humans, we are curious, we want to understand where we live, but as you also know, there's lots of benefits to it in terms of developing technology, telescopes, and eye and so on. And the landscape is very promising. This is the number, depends which plot you want. But if I focus, I look, say, this one, which is against here, you'll see there's almost like Moore's law that we make projects bigger and bigger. So this is the time, more or less, I did my PhD, and look where we are now. And those of you young and energetic, you're very lucky, but you'll have to probably work harder than us to analyze so many millions and tens of millions, hundreds of millions, even billions of galaxies. So, it is a golden age for the subject.
Just a
Hello?
Hello. Sir, just a gentle time check, about 5 minutes left.
Yes. Oh, so I have another 5? Okay, I'll finish in a few minutes here. Thank you. So, we have to really appreciate that time, but we may not have so much money in the future, We're already doing projects with $1 billion. are we going to get product for $10 billion? I don't know. So then also one cannot give a talk these days without talking about AI. I was very lucky to work on it already in the early 90s uh, uh, to classify galaxies and then to do photometric redshift. So I just want to mention that. And uh, also that, there's a lot of room, and I was very pleased to see the program of your conference that, there's a lot of room thinking, what does it all mean? Because it's one thing just to have another number. What does it all mean? And, when do you decide you put a new entity, like people hypothesized Neptune and it was found, but people also hypothesized Vulcan and it was not found, right? So we don't quite know. And there's a question, when do you stop? When do you think you know the answer? But you never know, because I thought that we know that it's just a cosmological constant until about a year ago, and now it looks maybe it's not. So I think you have to decide about it. So these are some thoughts with Joe Silk we had some years ago. And finally, because I mentioned the AI, and I know there are many young people in the audience, at UCL we started 9 years ago a program where the students are prepared to do a PhD in astronomy or particle physics, but also in machine learning. So they come out of the program with two qualifications, and some of them stay in academia, some of them uh, uh, go to industry, and actually part of the 4 years they spend 6 months in industry of AI. It could be a private company, or it could be a government department. For example, a student of mine went to the Treasury, another one went to do some analysis of fraud detection, right? So I think we'll see this happy connection between AI and cosmology, and I think we learn a lot from computer scientists, but maybe they can also use our data, which is public. It's not as complicated as data for health, and could be cross fertilization there. So this is actually my last slide, and my summary, based on current observations. This may change, of course. Based on current observations, Einstein was right that lambda exists, but he was wrong about its value. So the value we like today is something which gives acceleration, not gives static universe. Standard lambda CDM survived, 30 years, for 30 years almost. It's a big achievement, for a theory to survive so long. But it could be that dark energy evolving with time. And if it's true, then it's going to be paradigm shift. Okay, this will be a shakeup for physics. And it's definitely important to test lambda cold dark matter model further. And that's why we're having on the horizon Euclid and LSST. And it's going to be, really a golden age for cosmology. So this brings me to an end. Thank you very much for listening.
Thank you, sir. Thank you for this rigorous and deep talk. So now this is time to take some questions and answers. So the first question what I received from Kumar Ravi from Swami Vivekanand University, West Bengal. It seems that the need for dark energy arises specifically when we interpret cosmic acceleration within general relativity, as in the lambda CDM model and its extensions, where a negative pressure component is introduced by hand. In contrast, in modified gravity frameworks for intense FR gravity, the acceleration can emerge from the gravitational dynamics itself without invoking a separate dark energy component. So, is it fair to regard dark energy as a framework dependent construct rather than a physically established entity?
Yeah, thank you, Kumar, for this question. I think you touch on a fundamental issue here. Um, so I would say there are different schools of thought here. You can see, you probably, from the question, I can see you're very familiar with the literature. So, one can really stick to some sort of dark energy family of models from the beginning, and their scalar fields things like that, or one can do the kind of more curvature type f of r. There's a third school of thought which is more phenomenological, that you don't impose a model, and in a way this W0 WA is agnostic, right? It just says something changed with time. And yes, you're right, you're still using GR for that, but it's within that. And then once you have W0 WA, like those I showed, what do you do with it, right? You have to assign some physics to it. So that's my take on this. I think it's good to have all these approaches, ab initio approaches, and to maybe try f of r and to see what the difference is. I should say that I mainly focus with the oscillations, baronic acoustic oscillations, and with the standard candles, supernova, on the overall expansion of the universe. But it's also important to look at the evolution of clustering, because it would also be different if you have f of r or dark energy. So I think there's a lot still to do there. Thank you.
Shall we move to the next question? Okay, so Dev Dutt from Himachal Pradesh University Shimla. Can we detect dark energy with help of gravitational waves? Is there any experimental evidence regarding dark energy which is detected by gravitational waves?
Yeah, so that's obviously another exciting area, gravitational waves, which also was also predicted by Einstein. And as you know, a lot of work has gone into building instruments and so on. And the first detection was in, I believe, 2015. So it's over 10 years ago. Many experiments are going on, including in India. So already, if you remember, just from the one of the first detections, there was already a very serious constraint on what is the speed at which gravitational waves propagate. Okay, and there was there's this very strong limit that it's essentially like the speed of light. So this was very quickly, because there was the propagation of the gravitational waves, and there was also a signal coming 2 seconds after that. And from that, one can derive that speed of gravitational waves same as speed of light. It turns out that this by itself rules out many, many, many models as alternatives to gravity. At the same time, there are also people now thinking about, I just heard some discussion yesterday, people looking at all kinds of techniques, for example, pulsar arrays, which could also constrain differences in dark energy. So I think we're not quite there yet, that there are strong numbers, but we can certainly use gravitational waves for that. And last but not least, the binary neutron star at the time, if you remember, because we could tell also the distance of that, and the redshift was also used to get the Hubble constant. So indirectly, it's not directly dark energy, but it helps to pin down the Hubble constant. There's only one object so far, as a bright siren, as it's called, but there are many other dark sirens where you don't actually know you cannot exactly localize it. So altogether, this is not a test of cosmology through the Hubble constant. But yes, I think we should certainly flag that. Yeah, yeah.
Okay, so moving to the next question. It is from Dr. Bharat Pandey, Government PG College, Uttarakhand, India. Sir, I want to ask, Einstein introduced the cosmological constant as a fixed term, but could dark energy instead be evolving with cosmic time, indicating physics beyond Einstein's original idea?
Yes, so what I was trying to show you, that if we, if we look at the data, and if the result is W equals -1, it's Einstein's cosmological constant, but not the value he wanted for a static universe. It's a value which gives acceleration. On the other hand, if the measurements, as we have some hints of, indicate that it's not that the dark energy density changes with time, then, well, it could still be accommodated with general relativity, but we'll have to tell what is it. And is it left hand side or right hand side, right? We'll have to really understand that. I should maybe just make a remark for those of you who are practitioners to be very precise by my statements. When you say, does dark energy change with time? I didn't want to make the titles too long, so I just said dark energy. But I do mean the dark energy density, okay? In a centimeter cube with time, what's a change? And even if it's a constant W, but it's slightly deviated from -1, you'll get variation with time for density. Okay, you can see it from the equation I had on one of the first slides. So even if it's a constant, let alone if W is not a constant, then of course the density changes with time. Thank you.
Okay, so we have more questions. This is from Mr. Tejinder Singh, Tata Institute of Fundamental Research. Subir Sarkar and collaborators have argued that there is a cosmic dipole anomaly. The magnitude of the dipole is in distribution of radio sources disagrees with the CMB dipole. They conclude that the Copernican principle does not hold, and hence the inference of dark energy is questionable. Could you please share your view on their work?
Yeah, thank you. Well, I know and highly regard Professor Sarkar from Oxford. I know him well. And indeed, he and colleagues have pointed this dipole that you mentioned in the radio sources. There have been a number of papers on this. Again, it's a few. I cannot remember what is the current number of sigmas of deviation, but it's again something like maybe 3, 4 sigma. And it's always tricky. I work on dipoles in my PhD, by the way, way back with Lyndon Bell in Cambridge. And it's very tricky with dipoles. You're looking for a symmetry in the sky, and it's sufficient for some, systematics to upset things, if the calibration is not the same and so on. So I think it's great that Subir Sarkar and his colleagues are doing that. I think it's very good to check fundamentals. If it becomes a very strong event, maybe we can revisit it. But I would say I'd play I'd be the kind of a broad-minded skeptic here. I mean, it's good it's done, but I think I would not throw away the Copernican principle yet. Thank you.
Okay, so Mr. Ankur, his question is, what are the main systematic errors that could mimic the signal of evolving dark energy?
Yeah, thank you. So I think to be brief, I think this answer you have to answer it per probe. Okay, you cannot just give a global one. So let's start. I think baryonic acoustic oscillations is pretty robust because you just find the position of the peak. You have to do some corrections for the velocity field, but it's pretty robust. So I'd be surprised if there'd be a dramatic systematic found there, but you never know. Cosmic macro background, again, very precise experiment, and it's reassuring that 3 different experiments, Planck, ACT, and SPT, essentially give the same answer. But as I alluded to it, there's a paper by Saylor et al. That shows that, in the modeling of the CMB, you have many free parameters there. Then, if you put this optical depth to ionization tau, you change it, you may get something different. So you can think of it as a systematic to dark energy in the way you presented it. Probably the one that I feel a bit worried about, I mean, supernovae are amazing. They're amazing. And basically, they've done an amazing job, and the team leaders got Nobel Prize and all that. And broadly speaking, they were what the results will confirm. But supernovae are messy objects. There's a lot of physics we don't fully understand. I mean, we can explain about mass and so on, but what's going on exactly we don't know. Do supernovae vary if they are near the center of a galaxy or the outskirts? If they live in elliptical galaxies, spiral galaxies? So there have been many papers that looked for issues there. I think the good thing that new data coming from the existing protocol ZTF, Zwicky Transit Factory, and of course from LSST, although this would be higher matrix supernova, but the numbers will be so huge to be able to do it for different subsets, then maybe also the theory would get improved. Thank you. That's going to be a fertile area, understanding systematics. Yeah.
So this question is from Debjit. Quantum theory tells us empty space is filled with virtual particles. Is dark energy connected to quantum vacuum fluctuations?
Yes, so the at least hand wavy way of thinking about it, and I'm not a particle physicist, is really that in quantum mechanics, we know from the basic course in quantum mechanics, one of the bizarre elements of quantum mechanics that it gives an energy of the ground state of harmonic oscillator, half h nu. And then, so you can't, even the vacuum is energy, and then you can integrate it, and you get this 10 to the power 120 of the density. So that's very intriguing. I think it's such a big problem that people don't discuss it at conferences. It's a huge problem. And I think there's a connection there. There's a paper I really like, which appeared before all this data about dark energy by Steven Weinberg, 1989. And he goes through all these arguments. It's quite remarkable. He did it so early. So it has a nice section there about that. Thank you.
Anonymous one, I recently read the paper you cited. A strong progenitor age bias in supernova cosmology to alignment with DAISY bio and sign of a non-accelerating universe by Jason et al. MNRAS, the suggestion of a potentially non-accelerating universe seems to challenge the standard interpretation involving dark energy. Could you elaborate on how robust these signs of a non-accelerating universe are? Specifically, how should we interpret them in light of existing evidence from supernova and bio measurements, sorry, and do they point towards new physics or unresolved systematic in current cosmological models? I'm sorry if I not taken a few words properly.
No, that's okay. We say in the jargon, we say BAO, baryonic acoustic oscillations, but that's okay. Well, thank you for the question. I alluded to their paper very briefly. Son et al. It actually got quite a lot of publicity. It's a group that is based in South Korea. So there are two points here. One is it's very good that this group and other groups look into all these details. So they're looking at the correlation between the age of the progenitor, and they show some correlations. Okay, but I would say, and that's a view. I talk to people who do supernova for a living, people who do so. They tell me that the evidence for those correlations between the luminosity of supernova and the host in that paper are not strong. Okay, they may well be there. It's a quantitative question how strong it is. So that's the view of some supernova experts. But personally, I think it's very good that this group in South Korea and other groups are looking into this. And as I said, people look at all other correlations of with the environment within the galaxy and so on. I think it's all very good. Part of your question referred to the fact that it's true that if you take their procedure, fate as it is, they find that the universe is actually decelerating in recent times rather than accelerating. So that's an interesting comment. By the way, there's a combination of BO and CMB that also gives that. but it doesn't get much enough attention. So yes, there are two elements in their paper. One is, do they, is this correlation real? And if it's real, do we actually end up with a decelerating universe? So I would say it's food for thought, but supernova experts are a bit skeptical of the correlations. Thank you.
Okay, thank you so much, sir. This is very engaging discussion.
Yeah, I should say that all the questions were spot on. These are really questions
Yeah.
that we're all struggling with. So they're very good questions. So I appreciate that. Yeah.
Yeah. And sir, on behalf of the Bhaktivedanta Institute and all the audience, I would like to once again express our sincere gratitude to you for sharing deep research with all of us. I'm sorry this background sound. This lecture undoubtedly was both rigorous and deep. Even a non-physicist like me now understand how important the lambda phase is. Thank you very much, sir.